Presentation is from Cornell by Flavio Fenton, and he will talk us about low energy termination of fibrillation.
Thanks. I would like to thank again also the organizers, Nick, Sarah, Peter, and Richard for organizing this is a very, very nice meeting. And for some of you that may not know, we're like 148 or so registers now, and that makes the largest meeting ever done at the Newton Institute. So kudos to you guys. Doing very, very good job. On a more personal note, I also want to thank Olivier, because he took me to what I think is the best pub in the UK. So I had a good time there. Anyway, so I'm going to climb like 3 or 4 minutes because I lost them there. So I will quickly. I will talk quickly about why far field as a mechanism of defibrillation. I'll spend a little bit of time on what are virtual electrodes and how can they be recruited, and then I'll probably dash quickly through the examples of synchronization and termination. So termination of atrial arrhythmias are basically 3 standard ways to deal with them. Is atrial arrhythmic drug therapy, ablation, and electrical therapies. In electrical therapies, we have ATP, which works mostly for slow tachycardiac episodes, and electrical cardioversion, which is the more common. It requires that in the tissue, in order to work, it needs to be at least 5 volts per centimeter when you deliver the shock. So that means that when you deliver an external shock, you have to have between 100 joules or 360 joules, depending if it's monophasic or biphasic, which requires 1,000 volts, 30 to 45 milliamperes for 5 to 10 milliseconds. So it's a pretty strong shock. Internally, it still decreases to 7 joules, but it still is very painful. And not only painful, but it can also produce damage into the tissue. It can burn tissue, and better strategies could be desirable to have. So what I want to try to demonstrate is that cardioversion can be achieved using low field energy pulses, which require only like 1.4 volts per centimeter along the tissue. And when they're delivered at close to the dominant frequency of the arrhythmia. So if you compare, as I was saying, we compare it to 7 joules. If we go from 5 volts to 1.4, if we can reduce this amount, it's reduced about 4. It's a reduction of 1/4. The energy goes as square of the voltage. So this is a reduction of 16 in energy. So we go from 7 joules to 0.5 joules, which will be below the threshold of pain. Igor has presented also, he has a nice paper, it came out last month about defibrillation using a far field, but it's actually for tachycardia, where he used it 2 on-pin spiral waves. In this case, what I want to try to convince you is that what we're using the method here is actually for fibrillation to synchronize the tissue and eliminate the arrhythmia. So this is elimination by synchronization. And first of all, then I'll talk a little bit about what are virtual electrodes, which is what I'm going to use when you use far field electric fields. Plons in 82, he basically has a very nice paper which shows that discontinuities in conduction and conductivity can result in virtual electrodes when you produce an electric field. And now we know in the heart there are a lot of regions, possibilities for these discontinuities due to variations in fiber rotation. Abrupt rotation in fiber can produce some kind of discontinuities, especially regions where the divergency of the fibers is not 0. That's when the creation of the fibers. We have vessels. We have the extracellular matrix, which is only 4% of the total mass, but it actually it corresponds to a big chunk of the structure of the heart. So from the bidomain equations, one can actually observe, following Pronsi, how you can actually have this effect of heterogeneities, changes in heterogeneities, and conduction heterogeneities that can be in the mesoscale or the microscale level. So I'm going to show a simple example here, going in 1-dimensional, going through, so just as a circuit, either case for the mesoscale or the microscale is basically the same, just scaling. So you can go from boundary to hole to boundary, boundary to hole to boundary, and we just basically have, this is the intracellular, we have the extracellular, the intracellular, the extracellular, so you have boundary, hole, boundary. So when we produce a shock, we produce a current that propagates. Actually, I can use this. It propagates, and it propagates through the through the extracellular. Then when he finds a new pathway, well, of course, he's going to try to follow. He's going to divide with conservation of charge. But once it goes into the membrane, this is for resting membrane potential, but it's just a small charge. Well, it's going to change. Also, it's going to produce a change in polarity. So here it's going to hyperpolarize the tissue there. It's supposed to be blue, but then and then becomes isoelectric here because it's the same. But when it finds another path that has to come back in, comes in, and then it's going to produce another source sink. So now it's going to produce a positive minus. So it's going to become hyperpolarized there and polarized here. Same as you keep going. Then you find another hole, another boundary, and basically goes plus, minus, and minus, plus. So now you can see an effect that when you put a current, then you have the original electrodes, but you produce these little, what looks like virtual electrodes. So our electrodes are there, but is the effect of producing electrodes, but they are not there. But what you can see is that depending now on the resistance, the sizes of the obstacles, and the amount of current that you have, you can bring this hyperpolarization and polarization. You can increase it, so you can. This is supposed to be so now you can make it even larger in some places, depending on the current and the coupling. So you can bring the tissue such that the threshold of excitation is larger than the. I mean the polarization you produce is larger than the threshold for the polarization, and you produce an activation. When in other parts you may not be able to. Actually, these studies with virtual electrodes, then you can see that at certain values you can get these secondary sources. Secondary sources because you produce activations that are independent of the first sources, and has been studied by Vlad, by Igor, by Peter, by Natalia, among others. So let me just give you a quick example, just a proof of concept. We have a piece of tissue. We have two holes and a boundary, and we produce an activation. So if the excitation is very, very small, you're only going to excite. You're going to produce virtual electrodes on the three boundaries, but you're only going to produce activation on the largest. If you increase a little bit more the strength of the field, then you're going to produce activation on the boundary, but the next size of the tissue. And again, if you do it a little larger, then you can excite all the obstacles. So now this is now let me give you a proof of concept, but now in tissue and experiments using correlation and optical mapping. So we can take a ventricle, we can correlate to make a little bit of artificial boundaries. So we have two. Actually, so if we use an electric field of 0.18 volts per centimeter, you see that only excite the first boundary. Use the first boundary. It's very slow there. If we increase to if we split for 0.56, then we only excite also the edges of the obstacles. So now you can see as we increase the field strength from 0.18 to 0.93, you excite sooner and sooner the tissue. You get more excitation. Numerically, you can reproduce the same effect using a simulation over the tissue. Now, this is it was a proof of concept using large heterogeneities. Now, if we use a smaller heterogeneities, they can also produce virtual electrodes. So this is an example using collagen, and then we can produce an excitation. And then you see you excite the boundary, but also inside the tissue, you produce activation. If you increase the field strength, you activate more, you recruit more of these virtual electrodes and activate more. So you can see that, so the more virtual electrodes you recruit, as you increase the electric field, the time of excitation of the tissue is decreases as function of the electric field. So now, the idea is then if you can find the frequency of the arrhythmia and then pace at that frequency, you can synchronize the tissue and eliminate the arrhythmia. So this is a simulation where you have multiple spiral waves, and we're going to pace it 4 times. 1, 2, 3, and 4. And as you see, we eliminate the arrhythmia, and every time we're pacing, we're recruiting more and more tissue, and we're synchronizing the tissue to the new to the pacing cycle length. So, well, just let me just go quickly through. Basically, this is just summary of the effect that you can get as you increase the electric field. The time of activation of the tissue decreases. Experimentally, you can see it here in a canine atria. This is just pacing from a point stimulus. The time it takes to activate is 32 milliseconds. If you do an electric field at 0.32 volts per centimeter, then it takes 24 milliseconds. If you do it for 0.46 it decreases now. It decreases to 14 milliseconds. And if you increase it at 1.4 volts per centimeter, then it decreases to 12 milliseconds. So this curve here is a summary of 5 different experiments, and we can feed it, and we can see that the time of activation is kind of like follows an exponential of function of the electric field, like to the -1/2. How much I have? I have 5. Yeah. So anyway, so I'll go quickly through this one. If anybody wants to see more about the derivation of this, is a derivation of a scaling law using basically we can take an MRI, digitize. We have digitized four canine hearts at 200 microns, and then obtaining a normalized distribution of the discontinuities of the heart. So it follows this distribution follows a 1/r to the 2.5. So I won't go quickly because otherwise I will have time to explain some of the experiments. But when you do this asymptotic analysis, you ended up obtaining that using this distribution, you get that the time of activation goes as e to the -0.5, which is, as I remind you, is very close to what we see experimentally in the experiments. So so I hope I convinced you that we have this virtual electrode, that we can recruit them. And let me an example of now when you have we have AF on an atria, and we're going to pace 5 stimulus. This is the first, second, third, fourth, fifth, and you can you terminate the arrhythmia. Of course, if the stimulus is not strong enough, you're not going to synchronize the tissue. So this is a spiral wave that is actually contra-rotating, contra-clockwise rotating. We do the stimulus. We almost synchronize the whole tissue, but not entirely. And then there's, like Natalia says, this tunneling produces a new spiral wave, and actually produces a spiral wave that is now clockwise rotating. And so you need to have the right energy in order to synchronize. Where's the mouse? Okay. So now this is another example quickly of failure using 0.9 volts per centimeter. So it comes back the arrhythmia. This is success. And now comparing with one shock, this is one shock cardioversion failure at 4 volts per centimeter. Which is but then we increase to 4.6 volts per centimeter. There is a strong shock to depolarize the whole tissue. Now, if you calculate actually very quickly just the amount of tissue excited as function of time, you can see that during the during the pacing cycle length, you start when it's almost close, you start to synchronize. The derivative of this function actually tells you how synchronized you are, because it tells you how many they are exciting at the same time. So for the case that it doesn't work, it didn't work. It was starting to synchronize, but it didn't continue. For the case that worked, you can see that it's synchronized. Everybody got excited at the end at the same time, and then you just find out. For the one shock, what you see is that it's not synchronization, but it's a strong enough shock that everybody gets called to be excited. Some get earlier, some later, but everybody remains excited for a while until everybody remains, and then it terminates. So we have done this one, almost done. We have done this for different preparations using different amount of ACH to reproduce different types of frequencies, and in all of them we have been very successful. So just in summary, we have a success rate of 93% rate success on the experiments using 8 different dogs in 74 trials, and the energy necessary that we use is below is around 0.5 joules, which is below the threshold of pain. So I think it's a very good. It works very good, at least in vitro, but I don't know. For vitro, we need to. In vivo, we need to do more. I won't talk about this. We have done it in ventricles as well. But I just want to thank then Stefan Luther, who helped a lot with the. He designed the optical mapping system that we use. Elizabeth and Niels helped with the numerical simulations. And I would like to thank specifically Robert for teaching me how to cross the barrier between theory and experiments. Thank you.
Flavio, it's very interesting. We have done similar work, and in our hands, if you do a full three-dimensional reconstruction of the heart, in which you have, you represent the endocardial or atrial trabeculations and muscle strands that stick out of the endocardial surface. When you apply even a low-intensity shock, we never see any activations that are associated with blood vessels or anything within the myocardium that we actually segment out, so they are there. What is important is the papillary muscles, everything that sticks into the blood cavity. Fingers of myocardium of any type that stick in
I agree. Anything that changes the conductivity of the tissue.
Right,
those are
but it
important
isn't
ones.
the heterogeneities of types of collagen or blood vessels that give rise to that. So I was wondering, in your plot where you look at the heterogeneities, the scaling plot, do you account for the fact that we have a very non-uniform endocardium where you have heterogeneities that are larger than these sort of a blood vessel or collagen, which you described, that are actually really significant because blood is there and current is coming through the blood, through these, and coming out.
Right. But it just it's a scaling law that we get through segmented all the different MRIs and calculating tissue that is not the same conductivity. So.
But we have some data that shows, we didn't show it here, but that shows some of the sites of these activation of the virtual electrodes aligning with blood vessel network that we're able to reconstruct in the tissue.
Yeah, experimentally we can
Correct.
see that.
They're just not the first to activate. What I'm saying is, what activates
Yeah,
first
but
is
I mean-
something that doesn't have different conductivity, but it is
Yeah, we can
a
talk about-
myocardium that protrudes within the.
But what we care is that we can recruit this number, this
Right.
dysfunction of.
I agree with that. Yes.
At least for now, yeah. There's debate still who produces the activations, but the point is that we can recruit them and it works. Yeah.
I'm sorry, we need to finish.